Okay, so this example says an incompressible fluid of density rho and viscosity mu flows through a curved duct that turns the flow through angle theta. The cross-sectional area also changes. The average velocity, momentum, flux correction factor, gauge pressure, and area are known at the inlet 1 and outlet 2 as in the figure. Part A says, write an expression for the horizontal force F sub x of the fluid on the walls of the duct in terms of the given variables. Okay, so first step, define a control volume. I'm going to define my control volume as the fluid inside this duct. The problem is asking for F sub x, the force of the fluid on the walls of the duct. If I define my control volume this way, I will be able to kind of isolate that force term, as I'll show. So once I define my control volume, I'm going to write my conservation of linear momentum equation, which says the sum of forces in the x direction on the control volume equal the sum of momentum out, beta m dot v x, minus sum in beta m dot v x. Okay, so sum of forces acting on the control volume. I actually have three forces here acting on the control volume. I have the pressure acting right here. So my control volume is fluid inside the duct. What force is acting on the control volume? It's this pressure acting this way. Down here at 2.2, I have the velocity of the fluid moving kind of to the lower left out. That's with that arrow you see. But the force of the pressure there acting on the control volume is actually acting this way. And so I've got P2 over there. So the force at point 1 I have is P1 gauge times A1. Then I've also got P2 gauge A2. Now over here at point 2, my force is not acting in the x direction. There's a component to that pressure force that's acting in the x direction. So I need to multiply by some cosine of some angle here. The way I've drawn this, the x component of this pressure is going to be basically this angle. The problem defines theta here, and so I need to write this equation in terms of theta. This angle right here is 180 minus theta. So I could write that here as cosine 180 minus theta, or cosine of 180 minus theta is equal to the negative cosine of theta. So I could rewrite this as P1 gauge A1 minus P2 gauge A2 cosine theta. So I've just taken out the 180 minus theta, changed it to just theta, and put the negative here. So I'm just going to do that. Then I've got my F sub x. Here it's duct on fluid. Again, these are forces acting on the control volume. So it's the duct on the fluid. Then my momentum terms coming out of the control volume, m dot beta 2 v2 cosine theta, minus what's going in, m dot beta 1 v1. Now I'm going to just rearrange this to isolate my F sub x. F sub x duct on fluid equals negative P1 gauge A1 plus P2 gauge A2 cosine theta plus, and here I'm going to replace m dot with, m dot is equal to rho v1 a1, which equals rho v2 a2. Replace m dot with rho v1 a1, and then I've got over here beta 2 v2 cosine theta minus beta 1 v1. Alright, so I'm getting close, but the problem actually asks for f sub x, an expression for the horizontal force f sub x of the fluid on the walls of the duct. Here I've got an expression for f sub x duct on fluid. So I have to recognize that f sub x fluid on walls equals the negative f sub x duct on fluid from Newton's third law. And so that is going to equal the P1 gauge A1 minus P2 gauge A2 cosine theta plus rho V1 A1 beta 1 V1 minus beta 2 V2 cosine theta. So this is basically part A. Part B says verify your expression by plugging in the following values, and it gives me a bunch of values there. Okay, so the only value it doesn't give me here that is in my equation down here is V2. So I need to solve for V2. I know from up here that m dot equals rho V1 A1, which equals rho V2 A2. So V2 is equal to V1 A1 over A2. And so now I just go through and solve. Here I have V1 is 6. No. V1 is 10 meters per second. A1 is 0.025 meters squared. A2 is 0.05. Yeah, 0.05 meters squared. And we get 5 meters per second. And now it's just a matter of plugging in f sub x equals 78,470 newtons per meter squared times 0.025 meters squared minus 65,230 newtons per meter squared, which is P2, times 0.050 meters squared times cosine 135 plus rho, so we're going to plug in exact here, 998.2 kilograms per meter cubed times V1, which was 10 meters per second, times A1, which is 0.025 meters squared, times B1, 1.01, V1, 10 meters per second, minus V2, 1.03, times V2, 5 meters per second, times cosine 135. Okay? And if we do all that math, we should get that answer answer is 7,700 newtons. And because this is a positive value, that means it's to the right. Part C says, at what turning angle is the force maximized? Well, you can think about it a couple of ways. I mean, for one, the further this turns around, the greater the force. So 180 degrees is the correct answer. If we turn it from one direction to the other direction, that's the most force that we could have. Another way of thinking about it is by just looking at the equation and seeing that at cosine of theta, where if theta is 180 degrees, we're going to wind up with basically twice the linear momentum, or I should say adding our linear momentum terms. This term right here, because we have, let's see, right here, over here, because we have a negative here, if cosine theta is cosine of 180, then you're subtracting the largest negative you can. This becomes negative 1 times here, and you're going to be adding the biggest number there, and so you're going to wind up with the largest force. So that is the example problem.